We have been talking about the notion of density for subsets of Euclidean spaces for some real value s between 0 and n, and any subset of Euclidean space, we can define the S density, the upper and lower S densities to be precise, of the set E at a point x, not necessarily from E itself, by this lim sup, which captures, when zooming in around the point x, how much of the balls lie within the set E. If you haven't been watching previous videos, this is inspired by the Lebesgue density theorem, about which there was also a separate video. Okay, so we saw lots of examples and counterexamples. We drew some pictures to illustrate why the theorem here isn't too obvious. What it claims is that only under the assumption that the HS measure is finite, which again we emphasized why it is absolutely necessary to have such an assumption. So basically under zero assumptions, this upper density will be between 1 and 2 to negative s at almost every point of your set. And your set doesn't even have to be measurable, HS measurable. If it happens to be HS measurable, we have the second part that says the density at the points from outside the set must be 0, which is just intuitively the way it should be, because points not in this set shouldn't be seeing almost, the set shouldn't be seeing almost all of the balls centered at such points. We mentioned that the question of when we have this upper and lower density equal, which we also define to be that the density exists. So whenever we say density exists, it means that these two values are equal and finite. I think this is redundant given that at almost every point we already have this upper bound. But anyway, I gave you an example, in fact, showing that sometimes it can be infinity. And today's topic is a shocking claim about how restrictive such a thing is on the real value S and also on the set S. Suppose we have an HS measurable subset of Euclidean space with positive and finite HS measures. So E is truly an S-dimensional set. If density exists almost everywhere, by almost everywhere I would mean HS almost everywhere. So the only reasonable measure to consider in whatever we're talking about would be the same HS for the same value of S. So the claim is that if the density exists almost everywhere, then S must be an integer. And that is just amazing. It's one of the most remarkable theorems in geometric measure theory, and I personally was very shocked when I first saw this. The immediate question is always, why on earth? Why would not being an integer destroy any hope of having these densities equal? It's such a, to me at least, non-intuitive result that there's no such thing as, okay, if you move from an integer by just a tiny bit, there is some hope. There's absolutely no hope if you're not an integer. If you're an integer, of course, manifolds, smooth manifolds, give example where the densities actually exist. The second part to this is also quite interesting. So it says that the common value that means this equal to that. We could also drop just the stars and say whenever these are equal, we just drop the star and call it the density. That is actually the notation in Matilda, but just to emphasize, so this is saying that if these have a common value at almost every point, then the common value is equal to 1 almost everywhere. So this is saying that not only that equality of these upper and lower densities forces S to be an integer, it also forces that whenever they are equal, at almost every point, when the only common value would be 1. So you cannot have a function depending on x throughout your set E. Almost everywhere it is just equal to 1. So this being an upper bound for the upper density justifies this. So this is the biggest that it could be, and this theorem is saying that that will be achieved almost everywhere. For some historical remarks on this theorem, which originally was due to Marstrand in lower dimensions in the 60s, and then Mattila generalized it in the 70s, and the work of Price has improved a lot. This is not exactly that theorem, but a much deeper generalization, and yet more surprising generalizations of this are due to Price. So if you want the sharpest versions and some modern overview of what has been going on since then, this reference would be a great place to start. So in around March 2022, Mattila put out a survey about 112 pages or so dedicated to notion of rectifiability. So the reason this is so important to rectifiability is that the results of Price say that, and in this case, so they say under these assumptions, if the density exists almost everywhere, then you're at an integer dimension plus your set is rectifiable, which means ignoring a set of measure 0, the rest of your set is a countable union of C1 manifolds. And that's just a lot to claim simply because density exists. From the fact that just density exists, you obtain this much information about the set and how regular it is. So I want to complete this video by giving a concrete example of how upper and lower densities disagree. And the easiest way to do it would be that we go back to this counter set C delta that we constructed for any given lambda between 0 and 1/2, where in each step we only kept lambda % of the previous length, and in 2 segments. So this also gets divided like this, and we continue going down. Now the reason upper density and lower density here will be different is that, so of course for drawing purposes I'm doing them in different layers, but ultimately I will have a set, sorry about that, I will have a set sitting in just 0, 1. So my counter set, of course they are notoriously difficult to draw. We only just imagine how they would look like. Okay, so they will look like this, but let's say you take a point x in the counter set that will survive in all layers, in particular in this layer, and then I have to say it's this point. So you can take a ball of radius r, okay, and then a certain measure. So this set will have dimension equal to s, which is log 2 over log of 2 over lambda. It doesn't matter to us that much, just that it is strictly between 0 and 1. in particular it's not an integer. So hs of ball of x r, so suppose this is r, intersected with my counter set E, over r to power s omega s. So this limit, or rather lim inf, as r goes to 0, will be bigger than the lower density, lower s density. So this is in one particular instance of approaching 0. Lim in the lower density is the worst, the smallest values you can get. So in particular, this lim inf will be bigger than the lower density of E at x. But then notice that, okay, so what I meant, again, it's supremum versus the infimum, and okay. So sorry about that, fixing it right now. So this lim sup, okay, will be less than, okay, which is again for the same reason that upper density is the best you can do by approaching 0, by choosing the right sequence of radii. So this lim sup in particular will be less than that. Okay, sorry about this. So it's, maybe I should actually avoid specific calculations if I haven't prepared them obviously from before. So let's instead talk about the idea and forget about the particular calculations. So the idea is that if you take a much larger radius, of course to this side it will also be the same, your hs of E intersection with bxr, the larger radius, is not that much larger than if you had just x and the smaller radius. That's the point. So you increase the radius by a lot, but that doesn't pay off in terms of how much measure you see. Therefore, if you look at two sequences, in one of which you look at this over r to s, and the other one you look at r to s, the numerators are basically similar, but then the denominator, for example, we can always assume that this is at least 2 times the smaller one. So therefore this would there would be that gap between these quantities, and that gap would translate to upper density being strictly bigger than the lower density by some constant, which depends on this 2 and then the value s. So let's content ourselves with that. And in general, in higher dimensions, this phenomenon will occur whenever you have porous sets. So something like this, that there is always some empty space in between the pieces. We can look at self-similar type of constructions, and whenever you have these selection of balls that are kind of uniformly distributed, they don't accumulate, you have this porosity, this emptiness in between the pieces of your space, and that would usually lead to upper density being strictly bigger than the lower density. In particular, density doesn't exist. What that theorem we looked at is claiming is that this is the generic behavior, or not even generic, more than generic. This is the behavior always when you are not at an integer dimension. Okay, so hopefully you also found this theorem quite remarkable. Let me know your impressions if this is the first time you're seeing it. And yeah, so we will of course not go this fast into any proofs of this one, but as I promised before, it's worth looking at how the simpler density estimates are proved, because the techniques are quite interesting for other stuff as well. So until then, have a nice one, and happy holidays. But before holidays, actually, I will put other videos as well, so keep an eye.